Okay, in this video I would like to discuss about how to simulate HVAC system for a data center, which is very crucial in these days because of its intense use of data center. And we know that data center HVAC consumes a lot of electricity energies, so design it in a proper way will basically change the world, or like save the planet from overuse the energy. And on the other hand, of course, the good distribution of temperature and velocity in a data center data center HVAC system is very crucial for the performance of the data center itself, because it dissipates energy, and if it is overheats, you will make the performance lower. Okay, to do the simulation, we use tensorHVAC-Pro, which is a dedicated flow and thermal simulation software for HVAC application, which is easy to use for HVAC engineer, not designed for expert HVAC, so you don't have to worry about some CFD terminologies or CFD complications. Okay, let's just get started. So let's first create the project name. Let's say the data center trial XX, I don't know, just make some random name and save it in the place you want to save the project. Let's create the case, and here I want to import our model in the STL format. You can import it, you can generate the STL geometry from basically any simulation, basically every CAD software available in the market, like SolidWorks or maybe Revit or CATIA, Autodesk, Inventor, or maybe like SketchUp, Rhino, or anything else. Maybe I will also share these STL geometries if you want to try by yourself. So I will leave the download link in the link in the description of this video. Okay, let me import my model. Here we go. We get so many objects here. So here I will hide the ceiling so you can see the racks inside of this data center, and let me try to hide the wall so you can check the detail of these grills. So basically how it works is I have two inlets underneath this floor or top floor. Then this inlet blows some air in below this floor, and the air will push out from these grills, so it will flows toward these outlets. So we have hot aisle here and cold aisle here. So it's just like one simple example of data center HVAC. So we have some other scheme or other system that maybe basically we have have the similar setting in CFD. Okay, let's first define our geometries. The floor will be wall, ceiling also the wall. So for grill, because we have so many detailed grills, so we'll treat them as objects, not as wall. So basically if you select object, your mesh for this geometry will be finer. So yeah, if you use wall, maybe we cannot capture the detail of the grills holes. Okay, actually you can merge your STLs before you export, so you don't have to define it one by one. But in this case, I I don't separate them. I don't merge them. Instead, I separate them so I can input the unique values for each racks. Let's say if one racks have higher energy dissipation or lower, so you can just select it one by one. Okay, for the racks, I will also define it as the object, so it will have a nice mesh around it. So if you notice, we have detailed racks and also grills that if you are experienced in general application CFD software, maybe that will be very hard to solve with traditional meshing strategy like the triangle mesh. But in this tensorHVAC-Pro, we have some special meshing algorithm using block mesh and snappy hex mesh to easily generate this geometry. Okay, after all these objects selected, we can use the medium global mesh resolution, also medium object mesh resolution. You just simply hit the update mesh and you will get the the mesh you wanted. And after all done, you can check the mesh to make sure that your mesh is defined correctly. But I don't want to hit the update mesh here because it will take around like 10 minutes, so we will just skip to the next part. Okay, the next thing we will define is the boundary conditions. So let me hide again the ceiling and also the wall, so we can see how the inlets and outlets oriented. So the flow are from inlets move to the x direction. So here we define the velocity on the x direction for both inlets. For the temperature is up to you. Maybe I can use like 16 degrees Celsius. I don't know, it's just like some random number. You can vary these inputs to determine your best. That's the point of the simulation. You can do the iterations in just a couple of hours. No, you don't have to build the the physical system in the first place. Okay, we ignore the external wind flow, and for the objects, the driven temperature, it means like it will be depends on the environments. If you have 30 degree Celsius environment, so your object, in this case grill, will be also 30 degree. Or if you have like temperature gradient, it will follow that gradients. The T, of course, is like constant temperature. If you have constant temperature data, you can use this. But here for the grills, I will for the racks, I will define it as the temperature gradient. So here the temperature gradient is basically you can click here to check the basic theory. So it basically calculates the temperature gradient in the normal direction of a system based on the heat flux and also thermal conductivity. So you can calculate it using the calculator here, and also you can find some typical values you can use here, and you can input if you have your own data. But always do your own research. This value is just like for rough reference. Okay, here I will use 100, let's say, Kelvin per meter. I will define all of these racks with the same temperature gradient. And this is the reason why I separate each racks, because you can easily vary the temperature gradient. Or maybe if you have one rack with known temperature, you can use it as the specified temperature. Or if this rack, I don't know, turned off, let's say, you can just use the driven temperature. Okay, here we go. For the walls, maybe in this case we just ignore this, but in the real case, of course, you have to calculate the temperature difference between inside the building and outside. So you also have some temperature gradient, or if you have, you know, a specific insulation system, of course the temperature gradient will be also different. But maybe we in this case we just ignore this, because the rack temperatures are dominated, or maybe, you know, it's just like for the simplification. Okay, here we just ignore everything because we don't have to worry about the comfort. Yeah, of course we have to worry because maybe some person will go inside that room, but maybe will not be our main discussion here. Okay, for the setup solver, the start time is basically 0, so you are starting from the 0 starting point, and the end time basically tells you how many iterations that the simulation will be finished. So the larger the number of iterations makes your simulation more converts. It means the temperature distribution or maybe the velocity will not change with respect to iterations, which means a better result. But the larger the end time, it will takes more time for you and for your computer to do the simulation. So if you have, let's say, want to make the trial and error for like 10 designs, maybe you will better to use like smaller end time. But if you want a very precise result that will not change anymore with iteration, you have to put like maybe 10,000 or something. So yeah, in this case I used 20,000 to make sure that everything is not changed anymore. Don't forget to update the results. Here the right interval will determine how many steps the data will be saved. Let's say if I use 20,000 with 500, you will save around, I don't know, like 40 data, I guess. 20,000 divided by 500. Okay, the number of cores will determine the use of your internal core processors. So the larger the number will be faster, but of course it is limited by your hardware system. And if you want to use more cores, it means it will be slowing down other process. If you, let's say, you are working designing something 3D or maybe rendering something, it will slow down your system. It's your choice. And don't forget to update the setting and start running. But again, it will takes, in my system it takes a couple of hours, maybe 1 or 2 hours, I don't remember exactly, but we just skip this and let's open the finished project to make this tutorial faster. Here we go. We already finished with this data, and you just open the result on ParaView. Oh, sorry, it takes time to reconstruct the partition, so we will just wait for this to finish. Okay, here we go, our data center. So we can check the temperature here. maybe we can use the solid surface and change it to the feature edge to see what's happening inside. And here let's see how the temperature works by slicing these slice in the normal X direction, and you can see how the temperature and also velocity distributed. Here we go. Or if you want to see the rack's temperature, maybe you can hide the internal mesh. Instead, we will select the objects. The racks are basically the objects from, I don't know, 20 I guess to 30 something. Here we go. I think we have more racks still hidden. Okay, I think the 16 objects is just the grill. And change the color, also the surface, and here we go, we get our temperature to check the the temperature of these objects. And okay, let's go back again to our internal mesh. You don't have to worry about everything down here. If you check the internal mesh, you basically enable everything. I will make a specific discussion about how to use this para view, but at this time you just follow these steps. Okay, let's go back to our solid color and feature edge, and let's create streamline by using this button. And here we go, our streamline. You can see clearly how the air flows from bottom of this system and move upward to the outlet. And let's change this line a little bit to see how the air behaves. Let's try it here in some specific location. And yeah, it is more of an art compared to science, so you can explore by your own creativity. And yeah, that's it about simulation in data center. You can easily tweak your results. Let's say maybe change the temperature, or maybe change the velocity, or maybe evaluate how the flow behaves. If you want to make the flow cools first, you can see if you want to make the flow pass through these holes of these racks to cool it properly, maybe you have to put some barrier up here or something else. So you can basically make the decision based on this simulation. So maybe you can see some racks are not well cooled, and maybe some racks are just too cold. Maybe, yeah, the decision is based on this simulation basically. Okay, you can try this simulation software, tensorHVAC-Pro, or maybe tensorHVAC free version. I will give you the link in the description below, but please don't use that for the commercial purpose, because it's just for evaluation only. And if you have any question regarding to this video, or maybe you have any requests about other topics that you want to discuss, please let me know in the comment in the description below. Thank you for watching.